So thank you for this nice introduction. As the chairman said, my name is Jordi Muela, and I'm super happy to be here and present this work, parallel performance and communication pattern analysis on SOD2D as CFD high-order spectral element code. Just a brief outline of the presentation. First, I will say some words about who we are, the large-scale CFD group at Barcelona Supercomputing Center. And I will present you our new toy, the Mini-Symposium 5. And then I will present you our CFD code, SOD2D. I will show you scalability. I will talk a little bit about communication patterns. And if I have time that I don't know, I will talk a little bit about our experience with unified memory using GPUs. And finally, I want to show you SOD2D at work, although you already see that work in some previous presentations. So who we are? We are the largest scale CFD group. We are part of the Barcelona Supercomputing Center that we are located in this beautiful building in Barcelona, also nice city. And well, this is a little bit deprecated. Now we are more than 1,000 people working there. And we are a small group that we are part of the computer application and engineering group. And our main motivation, our backbone, our ikigai, our reason of being is to do larger scale simulations. We also love to solve the smallest scale of the simulations, okay? But by larger scales, I mean very large simulations. So our motivation is to do CFD codes that are able to run in the most new HPC architectures. We want to do CFD in this exascale era, okay? So this is our new toy, the Mini-Symposium 5, okay? As maybe you know, it has a general purpose partition based on CPUs and the accelerated partition based on the NVIDIA H100. And this is from the last top 100 list. And as you can see, the accelerated partition is in the 8th position, so not bad. We are in the top 10. While the Mini-Symposium general purpose partition, I mean, it's not so bad. We are the 22 of 500. But if you take a look to the numbers, you can see that the accelerated partition is giving us more than 5 times computational power and using only 0.7 the energy of the general purpose partition. So you can start to imagine why now everyone is installing GPUs. Okay, the energy efficiency is one of the main reasons. And with that, and also the fact that if you want to use the new HPC, you have to use GPUs because in the top 500, the first ones, only Fugaku is not based on GPUs. We wanted to develop a CFD code for large scale simulations, as we said, that is able to solve turbulent, compressible, and incompressible flows. And we want to be able to use GPUs and CPUs efficiently. So we wanted to develop this CFD code that can work efficiently in heterogeneous HPC clusters. And since we want to do science, we want to have a code with low dissipation because we want to run DNS and LES simulations. So the result was SOD2D, that is a continuous Galerkin high-order spectral element method code that can solve turbulent, compressible, and incompressible flows. And when SOD2D was born, when it was a baby, when we were pregnant of SOD2D, it was born as a mini app of the European project NextSim as a demonstrator of high-order methods for analytical applications. And yes, basically it was a code to solve the SOD shock tube in a 2D domain. But now that it's a teenager, now it can do more cool stuff and it can solve 3D simulations. So now SOD2D means a spectral high-order code to solve partial differential equations. Okay, and SOD2D is based on Fortran. Our GPU port path is OpenACC. You need HDF5 for input-output, MPI for the communications, JSON that allows the user to do the configuration of the case. And you can find it in this Git repo. We are open source, so please go to the repo, download it, play with it. We try to be as more responsible as possible. We love to do collaborations with other groups, as you can see. So please join us and enjoy with SOD2D. Okay, and very brief about the numerics because, well, already Jose Maria did a spoiler for me, but very brief. We are based on a spectral formulation of the continuous Galerkin finite elements model. we use Lobato-Gauss-Legendre quadrature points, okay? So the nodes are non-equispaced, allowing us to avoid the Runge effect. But since our integration points coincides with the nodes of the mesh, and we have this closed integration rule, this can lead to aliasing effects. So we use the skew-symmetric convective operator split, detailed by Kenny et al., to avoid this aliasing effect. Then the algorithm is stabilized using the entropy viscosity model proposed by Germont. And regarding the time integration schemes, we have these three for the compressible, fully explicit for order Runge-Kutta, then two lowest order Runge-Kutta methods, one of 5 steps and another of 14, and then an implicit explicit Runge-Kutta method where the convective is solved fully explicitly, and then the diffusive is solved implicitly. And regarding the compressible, we use the stable scheme, where basically the idea is that you solve the nonlinear term, the convective, explicitly using a third-order scheme, then you solve the Poisson, and finally, you integrate implicitly the diffusive term. Okay, so let's take a look to the interesting part of the work, which is the scalability of SOD2D. The main part of the study has been done in Mare Nostrum 5 in the accelerated partition, where you can see that each node has 4 NVIDIA H100. So here we have, first I have to show you which case I use it to do the scalability. Is the very well-known TGB case of low MAC. I have used different meshes of P order 4, and most of the cases that I'm going to show are run in float. Regarding when I have an implicit part where I use the CG, just to mention that we have a mixed precision. Okay, so results. These are the results for the fully explicit compressible for order. As you can see, we have an almost ideal scalability, both in the strong speed up and also in the weak speed up. So we are really happy with that. Here you have results up to 512 GPUs. And here I'm showing you the total iteration time. So you can see that only for these last cases, we have a small deviation from the ideal. And basically, this last row belongs to this load ratio. Here, I'm showing you the time per iteration normalized by the number of degrees of freedom per GPU and the number of Runge-Kutta steps. So what you can see here is that this deviation from the ideal scaling is not due to the increase of communication, that of course it has an impact that you can see, let's say, in the gap between these cases. But this deviation is because we are not loading properly the GPU. So you have to be aware that when you're working with GPUs, you have to load them properly, because if you not put enough load, enough degrees of freedom in each GPU, the GPUs are lazy and are not able to exploit all the benefits that they are offering to us. So that's really nice. And then just a comparison to see the portability of SOD2D. This is a comparison between Mare Nostrum 5, the H100, and then in Leonardo and Carolina that both have A100. So you can see that the scalability is almost the same, very, very nice. Of course, the H100 is a better GPU than the A100, so that's why it's faster. And if you wonder why Leonardo is faster than Carolina, basically it's because in Carolina, they claim that they have underclocked the A100 due to energy efficiency reasons, but the less power, less fun, you know. And then if we move to the lowest storage Runge-Kutta 5 steps, practically the same. We have a really good strong speed up, really good weak speed up. Basically the same conclusion regarding the relevance of the load ratio on the GPUs. Okay, just to note that we are a little bit more efficient. Okay, that before we were doing like 2-point-something nanoseconds per iteration, normalized by degrees of freedom and GPU. Now we are doing 1.8, but of course this is by the number of Runge-Kutta steps. So here we're doing 5 steps, not 4. So at the end, I will show you a comparison of all the schemes. For the Runge-Kutta of 14 steps, the same, fully explicit, almost ideal scalability. Here we are even more efficient, okay? But of course here we are doing 14 steps, not 4 or 5. And then when we move to the implicit, explicit Runge-Kutta in the compressible, you start to see that for the higher numbers, the scalability is not so ideal. I mean, I don't know what I have to put. This guy is an outlier, so my mistake. But you can see that, of course, still really good. We are almost all the time above 0.8, but you can start to see the impact of the implicit part, okay? How can you see the impact? Basically, you can start to see that when we have small load ratios, the gap is a little bit bigger. So the case that is using more GPUs, it will take more time than the one using less GPUs. But of course, the important for us is that if you are able to keep a good load, we are still doing a really good scalability. And then a comparison with Leonardo. Here, I do not have results for Carolina. And then when we move to the incompressible solver, here what you can see is that we do not only have the implicit part of the diffusive, but also the Poisson, that of course it has an impact on the scalability because you have more communications during the solving of the Poisson on the CG. But anyway, well, basically is what sorry. Yeah, basically is what you see when we have a small load ratio, we have this increase on the difference between the time that it will take running with more GPUs and with less GPUs. But still, if you are using, let's say, a lot of above 10 million degrees of freedom per GPU, our scalability is going to be really, really good. So we are really happy with that. Just a comparison with the other platforms, Leonardo and Carolina, and as you can see, really consistent. So we are happy because besides to having good scalability, we also are showing that we have good portability, okay? And then this is the one that I commented to you. This is just a comparison between all the time integration schemes, okay? And as you can see, for the implicit explicit, even the scalability was not so good, is practically the same that fully explicit time integration scheme. So really happy. And you only see the small degradation of the incompressible, but it's what it is. You need to solve a Poisson when you are working with incompressible, okay? And then all the results that I show you till now were for GPUs. But what about CPUs? Because we want to run in heterogeneous clusters, sometimes we run in CPUs. So these are the results. Ideal scalability. Why? Because here we do not have the effect of the load ratio on the GPUs. So basically, you are seeing here that the strongest speed up is almost ideal. Here is just a comparison between two different compilers, OpenMP plus GNU and NVIDIA HPC. NVIDIA HPC is a little bit more efficient, but the scalability is the same. And here, what I'm trying to show you is a comparison of the scalability on CPUs and GPUs. So you can see that the ideal scalability of the CPUs, while the small decrease or degradation on the scalability of GPUs, but almost ideal. And then what is interesting to see is that if you take a look to this point, what you can see is that, for example, if I run the same simulation, so this scalability is for the same simulation, of course. If I use 896 CPUs, I will need 2 seconds to do one iteration. If I use 16 GPUs, it will take like 0.2 seconds to do the same iteration. So if you do some rough numbers, that means that I will need 560 CPUs of the Mare Nostrum Pi general purpose partition to do the same job that one single NVIDIA H100. Basically, if you take into account that each node of Mare Nostrum 5 has 112 CPUs, that means that I need 5 nodes of CPUs to do the same that one NVIDIA H100. So that's good reason to use GPUs, okay? And well, this is just very recent results from the last week or the last few days. Now we have this is not a TGP case. This is a quite complex mesh from the NASA High-Leaf Common Research Model. So it's a complex airplane. It's a mesh of almost 5 billion degrees of freedom, okay? And we were allowed to go up to 2048 GPUs. For the moment, we have asked for more GPUs, but the guys ruling the Mare Nostrum 5 queue say no, because this is almost the half of the GPUs of the Mare Nostrum 5. So we were allowed to go till that number. We have to run in double because of the mesh, okay? And you can see that this is run with the implicit-explicit Runge-CUDA, okay? Very good scalability up to 2048 GPUs. So we are quite happy with the results, okay? And now we can move to communication patterns. This is a study that we did when I was developing the parallelization of SOD2D, okay? As you know, when you are running parallel simulations, you need to exchange data between the different ranks, okay? So in MPI, you have the classical point-to-point communication, the send-receive or asynchronous send-receive. You also can use the one-sided, so the MPI put, the MPI get, and we were trying to see which was the most efficient in our case. Then also we tested if we use or not CUDA-aware MPI. What is CUDA-aware MPI in case you don't know it? Basically, when you are running in GPUs and you don't use CUDA-aware MPI, when you want to send data, you need to copy the data on the GPU to the CPU or the host, then you do the MPI communication, and then this processor copy the data back to the other GPU, okay? But if you have a code that is CUDA-aware MPI and your hardware allows CUDA-aware MPI communications, then you can send the data directly from GPU to the other GPU, okay? For example, this is a code with no CUDA-aware MPI, so I need to update the host information, then I do the MPI send receive, and basically then I copy back the information on the device. On the other hand, if I have MPI CUDA-aware communications, then I just do the MPI send receive with the data on the GPU. We also compare the communications with the ones provided, the MPI communications with the one provided in the NVIDIA Collective Communication Library, so Nickel, okay? A very recent implementation from NVIDIA. So here, well, I'm not doing MPI send receive or MPI put or MPI get. I'm using Nickel, so I have to do Nickel receive, Nickel send, and then this is supposed to be direct from GPU to GPU. And then the results. What can we see? For example, this is for 8 GPUs. Take a look. If you use C, the C is for CUDA-aware, and when I do not have the C, is non-CUDA-aware. So you can see the difference between CUDA-aware communications and non-CUDA-aware. As we were expecting, basically go CUDA-aware because it has a huge impact on the communication time. This is for the Nickel. So you can see that the MPI CUDA-aware is faster than the current implementation of Nickel. And the same is true when we increase, okay, I will go faster. The same is true when I increase the number of GPUs, okay? So at the end, the default communication scheme for us is the asynchronous send receive. Although put and get are also performing really well, at the end, the asynchronous send receive is the one working the best for all the cases. This is just a comparison with an all Mare Nostrum 4 cluster, just to show you which is the effect of working with a very new cluster with all one. It was not a bad cluster, now dismantle it, but you can see which is the impact on the communication speed. Also very curious that in this old cluster, which is not happening in the new one, is that when I was increasing the number of GPUs and for very small meshes, at some point the non-CUDA-aware was performing better. But anyway, these cases were not realistic because in this case, the degrees of freedom per GPU were very small. And then I have to avoid this because I run out of time, but just I can skip everything of that, okay? Blah, 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 blah. Just if you start to work on a GPU code, starts programming with unified memory, but once your code is working, then move to do the manage of the memory by yourself because the increase on the performance can be really huge. And that's it, you can keep with that idea. And just to end, just This is SOD2D at work, okay? This is the CRMA, the dry fire, some wind farms, and thank you. Sorry to take longer. That's it. Thank you so much.